All right, welcome back to the accumulation functions lesson, where we are going to be solving some more contextual problems using some accumulation functions, some integral accumulation functions. And of course, the picture here is referring to that notorious AP question that we did in the warm-up, where there are 0.7 person per second leaving the escalator. All right, and so again, this is pretty much free response question based, but let's review some accumulation function stuff that we talked about before. So that whenever we're talking about accumulation function, is what we're doing is our function itself is defined based on an integral, and that integral has as one of its upper limits some sort of variable, and it's the variable for the particular function. So this f of x is equal to the definite integral from 3 to x of negative 2t dt. That's our accumulation function. What's it accumulating? Of course, it's accumulating some sort of area underneath the curve negative 2t. Now remember, for these particular equations, that we have two different variables going on. The variable for the function is x. Inside of the definite integral, we have t, so that those two variables don't get confused. And you shouldn't do those either. All right, so what we're doing is we're looking at this next question here, example 1. Let g be a function defined on the closed interval from negative 6 to 6 with g of 0 equaling 3, such that g of x is equal to 3 plus the definite integral from 0 to x of f of t dt. And the graph of f consists of one semicircle and 4 line segments, as shown in the figure below, over here on the right-hand side. So you can see that g of x is defined as an accumulation function, and what it's accumulating area under is the graph of f as it's given to us here. Part A, between negative 6 and 6, find all values x at which x has a relative minimum. Part B, between negative 6 and 6, find all values of x where the graph has a point of inflection, and justify your answer. And we got two more parts here. Find all intervals on part C on which the graph of g is concave down and increasing. And then finally, find the absolute maximum value of g of x over the closed interval from negative 6 to 6. Sounds a little bit like the closed interval test. All right, let's scroll back down here to this first example, and I've copied the graph again, and here's the first part of the equation, or the problem. And I'm going to go ahead and write down, this is example, wait, this is the wrong color, I don't want this one, I want this one. 1. And our equation had this initial condition, g of 0 is equal to 3, and then g of x was equal to 3 plus definite integral from 0 to x f of t dt. And again, you can notice the difference in the variables. X is the variable for this function. It's the thing that's going to accumulate area as we move to the right, be positive, or accumulating area, taking it away, moving it towards the left there. Okay, so part A, find all values of x which g has a relative minimum. Let me move some of this other stuff down so I have more space to work. In order to find a relative minimum, we need to look at the derivative. So step number 1 is to take the g of x function and take its derivative. So g of x again was 3 plus definite integral from 0 to x f of t dt. Take its derivative. As we've done before, taking the derivative of an integral equation, those two things are inverses, and so we get our original equation back with a change of variable. We're just going to take this x and poke it in here for the t, f of t. And this is super important. This happens all the time on the free response section of the test. That needs to be on there someplace. That's probably going to be worth some sort of point. The graph that we're given here is actually g prime of x. So this turns into one of those question types that we've done before, where we're looking at the derivative graph in order to draw some conclusions about the original function, right? It's just phrased in a different way. It's phrased as an accumulation function. Okay, so to find the minimum values, we need to find its critical numbers. So its critical numbers, I'll highlight here with green. Critical numbers happen where our derivative is equal to 0. And I definitely want to state that. So we want this thing to be equal to 0 for our critical numbers. A lot of times that is worth a point as well, where you are making that consideration. Now, as far as minimum goes, how do I get a minimum? So a minimum's got to go like this. It's got to change from decreasing to increasing. This means our derivative changes from negative to positive. Changing from negative to positive, I've got to get rid of some of these because the first one goes from negative to positive. Here, let me highlight that. Negative to positive, that's good, but the next one doesn't. It goes from positive to negative. Get rid of it. Okay, the next one that's at positive 2 goes from negative to positive. It's good, but the last one here at 5 is positive negative. It's a relative maximum. All right, so let's write it up, our conclusion here. G of x has relative minimums at, that isn't how you spell that word, minimum. Okay, I don't think that's how you spell it either. It's just right there, just copy it. At x is equal to, that looks like it's at negative 4, and x is equal to positive 2. And now we need to justify it always, since g prime of x, which is equal to f of x, changes from negative to positive. At these values. So here are two answers for this particular question. Boop. Right, and then providing that justification, it's essential. All right, let's look at part B. Part B, enlarge it a little bit, boop, and get rid of all these other things. Move, you're gone. Between negative 6 and 6, find all values of x at which the graph of g has a point of inflection. So there's a couple of ways to justify a point of inflection. So we're usually looking at, not Q, G double prime. Now it's not enough to say that G double prime is equal to 0. That's not enough. We have to have G double prime changing signs. It changes signs from positive to negative or negative to positive. We don't have to specify necessarily like we did for relative minimums. Because a change in sign in the second derivative indicates a change in concavity. The issue here really is that I don't have G double prime, I have G prime. Well, we can still justify a point of inflection if G prime changes from increasing to decreasing, or vice versa. And that's actually how I would recommend that you justify it, because that's what you're given. You're given a graph of G prime of x, so let's justify it based on that one. And anyway, that's the definition of points of inflection anyway, or concavity anyway. And then the second derivative changing sign is just a convenient test for it if you have access to your second derivative. So let's look to see where does G prime change from increasing to decreasing or vice versa. And I'll get rid of some of these markings that we've already made on here. Okay, so we've got increasing here, and then on the other side we've got decreasing. Boop. Maybe make a color that's a little bit different from that. There we go. So it changes from increasing to decreasing at -3 it looks like. And then it continues to decrease, even though there's little kinks in it, doesn't matter. Let's see, it's decreasing, decreasing, decreasing. And then right down here, we have another one at 0, right? Because we are changing from decreasing to increasing again. So we have one here at 0. And it continues to increase until we get to 1, 2, 3. And then after 3, it decreases again. So we've got 1, tool, go away, 3 points of inflection. We've got -3, +3, and 0. And the way that I want to phrase it, again, is in terms of the first derivative, which is equal to the graph of f here, is changing from increasing to decreasing or from decreasing to increasing. So at both -3 and +3, it's increasing to decreasing. I'm going to do these two separately. The graph of g of x has points of inflection at x is equal to ±3 because the graph of g prime of x, which is equal to f of x, changes from increasing. Actually, let's write that word out. To decreasing. Okay, and then we had one more. We had one at 0, and this is where the graph is changing from decreasing to increasing. So I'm going to put that one separately. After I move this stuff away. Okay. The graph of g of x also has a point of inflection at x equals 0 because g prime of x changes from decreasing to increasing, I think it was. Now, you don't have to separate those. You could have said that the graph of g of x has points of inflection at ±3 and 0 because the graph g prime of x, which is equal to f of x, changes from increasing to decreasing or decreasing to increasing, or maybe even the words vice versa. I just wanted to separate them for the purposes of being super thorough because we've got the time. We've got all the time in the world. Let's look at part C. Find all the intervals on which the graph of g is concave down and increasing. What I want to do is actually, let's get another picture of the graph in here. And I think I got one right there. There we go. So, concave down. Concave down is going to happen when our derivative is decreasing, as we were talking about before. So our derivative is going to be decreasing. Let's see. Here and here it's all decreasing, and then over here it's all decreasing. Okay, and then the other part is when is g increasing? G is increasing when its derivative is positive. So let's switch colors again. So derivative is positive just means it's above the x-axis. It's this portion, and then finally this portion. So those are the two parts that we want. And we just have to give some sort of justification for it. So the graph of g of x is concave down and increasing on the intervals. Now, usually for increasing, you put closed intervals, but since we're including concavity in it, we're going to keep this on open intervals. On the intervals, let's see, this first one is negative 3 to negative 2. And then we have, let's see, 3 to 5, it looks like. 3 to 5. Since g prime of x, which is equal to f of x, is both, let's see, for concavity, decreasing, and then for increasing is positive, and positive on these intervals. And that one is done for sure. All right, we only have one little section left on this, part D. Part D, this one should be super fun. Find the absolute maximum value of g of x over the closed interval from -6 to 6. All right, we've seen this 4 billion times. Absolute maximum indicates that we need to do a closed interval test. Closed interval test, it just looks like a table of values, and in that table of values we've got critical numbers and we have endpoints. That's where the absolute maximum and minimums can happen. So let's go back to our graph, clean it up a little bit here, get rid of all of this garbage, and then let's take a look. We've got endpoints here at -6 and +6. We want to make sure that we include those things. And then we also want our critical numbers. So we've got our critical numbers at -4, -2, +2, and at 5. But can we eliminate any of those? And I think that we can. Like, for example, we can eliminate, maybe use a blue here, we're looking for absolute maximum, so we can get rid of any of the relative minimums. We can get rid of, at -4, because the derivative changes from negative to positive, that one is a min. Okay, and then likewise, we can get rid of the one at 2 for the exact same reason. Derivative changes from negative to positive, there's another minimum. Right, and so we basically have 1, 2, 3, 4 things to check. And in order to actually find each one of the values, we need an equation, so we can stick our critical numbers back into the equation and our endpoints back into the equation. And it'll look something like this. It was the same equation that they gave us, that g of x is equal to 3 plus the definite integral from 0 to x of f of t dt. Okay, so we have our values, and I'm going to write them over here on the right hand side, that we have, and notice that we did eliminate. We made some sort of note that we eliminated both -4 and 2 because those are relative minimums. So we're going to only consider the x values of -6, -4, no, we eliminate that, -2, and 5 and 6. It's going to shortcut this considerably, and then we want the g of x. And the reason why we want to shortcut it, because we have to find areas and stuff. That's how we're going to interpret, of course, this portion of the accumulation function. It's accumulating area. And this was a calculator inactive problem. That's why they gave us straight line segments and a semicircle, so that we could very easily find the areas of each of those pieces. So let's just go ahead and do that. Let's find the areas of each one of these pieces. And I'll like color some of this stuff in here. Maybe red for the stuff that's down below. So let's first find the area of this piece. It'll probably come up. So the area here is, it's a 1 by 1 and divided by 2, so it's a half. Okay, and then another part that's down below is the semicircle, looking like a bit of watermelon. its excuse me, its radius is 2. So this thing is 1/2 pi times 2 squared is 4. So it is 2 pi. So in other words, this part's pi and this part's also pi. But they're negatives because they're down below. This one's also -1/2. I should have written that. And then we've got one more piece that's down below. That'll probably come up. This one is a 2 by 2, which is 4. Take half of that is 2. So again, a -2 for this portion. All right, and then we have two triangles that are up above. I'm guessing they should be blue. So here's one. It is a 2 by 1, so that's 2 times a half, or we can just see there's two little halvesies right there, so that's a +1. And then we've got one more little piece, triangle. Okay, base here is 1, 2, 3. It's a 3 times 2, which is 6. Take half of that, which is, this one is a +3. All right, I think that we're ready. I do think that we're ready to now evaluate each one of these values, -6, -2, 5, and +6 for our closed interval test. Let's do, start with -6, I guess. 3 plus the definite integral from 0 to -6 f of t dt. Now, on this definite integral, notice that our two limits of integration are in the wrong order. How do we switch them? We can switch them as long as we negate our definite integral. So this is 3 minus the definite integral from -6 to 0 f of t dt. And again, I'm doing the definite integral part as the area. So we've got 3 minus, and then I'll put in parentheses all of these area pieces. And we're going from 0 to 6. So starting at 0, I have this -pi, I've got this +1, and I've got this -2. So inside the parentheses here, -5, or -pi, +1, -2, I think it was. All right, and then distribute, combine some like terms. So this is a -1 inside here. 3 minus a negative, so +pi, and then +1 gives us 4 plus pi. All right, pretty much done, right? Not right. We got -2. 3 plus the definite integral from 0 to -2 f of t dt, and we can see it's backwards again, so we got to switch it and negate it. -2 to 0 f of t dt, and we've got 3 minus, put in some parentheses, and we're just going from 0 to -2, so it's just the pi part that's right there, the -pi part. Distributing that negative, we get 3 plus pi. Ooh, so close. Those were so close. Okay, keep going. We're almost there. And like halfway there, I guess. And it looks like I'm about to run out of space, so I'm going to put an extra page right up in here, so I don't have to worry about it. All right, let's do g of, what do we got? 5. 3 plus definite integral from 0 to 5 f of t dt. Okay, so this one we don't have to compensate for because they're in the correct order, so we can just write 3 plus, and then whatever the areas are with the signs that the graph actually has on it. So we're going from 0 all the way up to the 5. That's going to be the -pi here and the +3 right there. A -pi, what did I say the other one was? 3 plus 3, which is equal to 6 minus pi. 6 minus pi. Okay, so as far as this goes, this is about 3. Pi is about 3, so I'm subtracting about 3. So this one is 3-ish. So we can still see that this thing is bigger because that would be about 7-ish, right? Okay. And then we have one more to do, and this is at positive, 6, which is 3 plus definite